Maths 306. We're now at part 3. In this part, we'll be treating homomorphic images, kernel, image of a homomorphism, first and second isomorphism. And we begin with the definition of what a kernel is. Now, anything, so if you suppose you have a map theta and it maps, say, from G to G prime. So anything, say G, any element mapped to 1. Now, the collection of such elements is what we call the kernel. You see G is in capital G and it is taken to 1. Okay, so all elements of this map that are taken to 1 are all in the kernel, and the collection of such elements is called the kernel. Okay, next is the image. So the image of theta is basically those elements that are mapped. Okay, you don't actually need to know where they are mapped to. Okay, so that's the image, okay, of theta. So we go straight to a lemma. In your lecture notice 1.12, it says that if you have a map theta from G to G prime and it's a homomorphism, okay, so you know what a homomorphism is. That's theta. If it takes x, y, it'll take it to theta of x and theta of y, right? Okay, so that's homomorphism. So it satisfies, this theta satisfies that condition, okay? So it says if we happen to have a map, it's a homomorphism, and then it says that once you have a homomorphism, that the kernel is normal. It's a normal subgroup, not only normal, it's a subgroup, a normal subgroup of G, and that the image of theta is a subgroup of G prime. Now for this aspect, this part of the lemma, I will leave it to you. Students are to do this. It's for students. Okay, it's in your hard copy of your lecture notes, but I won't be taking it in this video, so you ensure you go and study and find out how to prove it. So I will be taking the kind of normal subgroup here. Okay, so we want to show that the kernel of theta is normal. To do that, we need to show first that the kernel of theta is actually a subgroup of the group before we can even show that it is what? Theta is normal in G. So what are the conditions for something being normal that I told us in our previous videos? We said we should check that that thing is not empty, so we are checking that the kernel is not empty. That if we happen to have it not empty, it means that we can find elements, right? So we can find elements, say x, y, in the kernel, because that's what we want to show. It's the kernel we want to show that it's normal. It's a subgroup. So if we can find this, we will now check if y inverse is in x, the kernel of theta. We'll also check the xy inverse in the kernel of theta. So that's for subgroup, right? And finally, if something is normal, if you remember, we said a subgroup of a group G is said to be normal if the left coset equals to the right coset, recall? So, and there was also other definitions like G inverse of capital H, if you remember, being elements of capital H. Do you remember that? Something like that. We did that. Okay, so in that case, based on that definition, because we want to prove it mathematically that it is normal, we would use this definition, that if you pick G inverse of the kernel, K being in the kernel and G, that will get it in the kernel of theta. So that's our intention. So we need to show these 4 properties and confirm if they do exist. So we want to take the first one now. Okay, so for the proof of the first identity, which is that the kernel of theta is not empty, this is true because you already have shown in one of our previous lemmas that 1 theta equal to 1. That is, 1 is always taken to 1. And remember the definition of a kernel. What did we say it was? We said that the kernel was a collection of all elements mapped to 1. Is that not so? So we are seeing now. Sorry, I've taken us way ahead of us. Okay, so we are seeing that the kernel is not empty based on that, because 1 theta equal to 1. So kernel of theta 1 is in it. So therefore, it's not empty. So we proved 1. Is that not so? So to prove 2 now we know it's not empty. It means we can find x and y in the kernel of theta. And if x and y are in the kernel of theta, it means it satisfies the condition that x is taken to 1 and y is taken to 1. Do you agree? Anything in the kernel, remember we said is taken to 1. If you remember, I said if g is mapped to 1, then g will be in the kernel of theta, right? So if you now have x in the kernel of theta, it means that x will be equal to 1. If y is in the kernel of theta, y will be taken to 1, or y theta will be equal to 1. Okay, so we found x and y in the kernel of theta because the kernel of theta is not empty, 1 theta equal to 1. So this satisfies this condition. So we now want to show that we can find y inverse theta. So what will y inverse theta be like? Already you have seen before now that x inverse of theta is the same as x theta inverse, you remember in our previous proofs. Okay, so if y inverse theta is this, it's definitely going to be y theta inverse based on this identity, right? Okay, so that's how we got that step. Okay, so now we know y inverse theta is the same thing as y theta all inverse, but we know what y theta is. See it here, we said it was 1. So wherever there is y theta, we just simply put the value 1 because y theta is 1. See it here, right in here. Okay, so y theta is 1. So what is 1 inverse? That's just 1. So automatically we have shown that y inverse theta takes, so y inverse is taken to 1, and therefore y inverse lies in the kernel because the kernel of theta collects everything mapped to 1. So we proved the second identity. Okay, the third identity now. What are we to show in the third identity? We said we will show that x, y inverse theta. We want to check if to give us 1. That's our target, because if it's in the kernel, it will go to 1, right? So let's say if it will give us 1. Okay, so for the third identity, xy inverse is the same as x, y inverse theta y, because we know theta is a homomorphism. It splits terms, is that not so? But you have seen, because x and y were in the kernel, it goes to 1. And this y inverse theta, we just proved it in the previous proof here. We proved it to be 1. Okay, we did that. So this is also 1. And 1 times 1 is just 1. Oh, automatically you have shown that x, y inverse of theta is going to go straight to the identity. Therefore, this term is in the kernel of theta, as you can see here, which proves the third identity. Okay, so if I'm too fast, you can play, rewind, and go back, pause as you keep going to see and know what we've done thus far. Now there's a fourth identity, because so far so good. If we've satisfied point 1, we satisfied point 2, and satisfied point 3, it means that we've succeeded in showing that the kernel of theta is a subgroup of G, right? That's all we've done. We've not proven that it is normal, because that's what we were told to do. So now to show that this is normal, we need to prove the fourth condition, which is that G inverse KG lies in kernel of theta, where G is from capital G, the G inverse are capital G, and K is from the kernel of theta. Okay, so let's see what happens. So we put theta act on this our relationship, and because theta is a homomorphism, it splits it, right? So it splits them 1 for this, each one of them gets its own theta. Okay, so it splits them nicely, and we already know what this is. We already know what this is. K theta is in the kernel. What happens to it? It goes to 1, right? Because K is from the kernel. That's why this disappeared and became this. And then G inverse G, because we're working with group identities, we know this is already G all inverse, right? And then GG. So if this is G inverse and this is G theta, this goes to 1 automatically because of the group identity. So automatically we have shown that G inverse K G, when theta acts on it, goes to identity, meaning that this thing lies in the kernel of theta. What does that mean? It means that we succeeded in showing that the kernel of theta is normal. Is that not so? It's normal. It satisfied the condition of normal being normal. So with the point 1, 2, 3, and 4, you can, the statement holds, that is, that the kernel of theta is not just normal, but it's also a subgroup of G. That's what we have there. that you've shown the idea proof. Okay, so you will need to be able to state these isomorphisms by heart. I don't need to prove it. For now, we will not worry about the proof of the theorem. So you need to be able to state the first isomorphism theorem, meaning that if you have a map G to G prime two groups, and it's a homomorphism of groups, then G modulo the kernel of theta is isomorphic to the image of theta. Okay, so G modulo kernel of theta is isomorphic to the image of theta. So that's what the first isomorphism theorem states. So you have a map theta, and it takes G to G prime, and it is a homomorphism. Then it satisfies the condition that G modulo the kernel of theta is isomorphic to the image of theta. The second isomorphism theorem that you will need to be able to state says that if you have G to be a group and H to be a subgroup of G, and G has a normal subgroup N, then N, the product NH, is a subgroup of G, and the intersection of H and N is normal in H. Furthermore, if this happens, you have that the product NH modulo N is isomorphic to H modulo H intersection N. So you need to be able to state these theorems by heart. So I think with that, that's what we'll be doing all through this video. So prepare, study. If you have questions, ask on the WhatsApp chat. Thank you.